everyone present. It gives me immense pleasure to extend a warm and heartfelt welcome to this gathering on the occasion of the inauguration of a faculty development program. Faculty development programs are vital platforms for us as educators to renew our perspectives, explore innovative teaching methods, and keep ourselves updated with recent advancement in our respective domains. They not only enhance our professional competence but also equip us to inspire and empower our students better. I am confident that this FTP will provide each one of us with fresh insights, meaningful discussions, and valuable takeaways that will enrich our teaching learning processes. Now, first and foremost, I invite God the Almighty for this grateful presence and guidance for this FTP program. I also take this opportunity to welcome our respected chairman, Engineer F. Princevino, Principal Dr. C. Sudhakar, who has always been a guiding light and source of encouragement for all our academic endeavors. Next, on behalf of our institution, Macetatalfdp College of Engineering and Technology, I feel honored to welcome all the speakers who have accepted our invitation, and we are deeply grateful to you for joining in this journey. I take this opportunity to welcome our staff members who have supported us and encouraged us with this event. I also am very glad to welcome all the participants who have joined us in this journey. Welcome you all. Now, I respectfully invite our beloved principal, Dr. C. Sudhakar, to kindly deliver the inaugural address.
Good evening, respected chairman, respected chief guest, distinguished resource persons, faculty members, and dear participants. Very good evening. It gives me immense pleasure to welcome you all to the inauguration of this ACT Training and Learning Academy sponsored online faculty development program organized by Department of Science and Humanities, Macetatalfdp College of Engineering and Technology on the topic Advancement and Application of Smart Materials in Environment and Technologies. At the outset, I extend my warm greetings and heartfelt gratitude to our respected resource persons who have kindly consented to be part of this program and share their valuable expertise. Faculty development programs plays a vital role in enriching the academic and professional capabilities of teachers. In the rapidly evolving landscape of higher education, it is imperative that we as educators continuously update our knowledge, refine our teaching methodologies, and embrace innovation in pedagogy, technology, and research. This FDP is designed with the objective of providing a platform to the exchange of ideas, gain insights from experts, and enhance the teaching learning process in alignment with global standard. The theme of this FDP is particularly relevant today as it addresses the challenges and opportunities that lie ahead for teaching community. I am confident that the sessions will equip us with fresh perspectives, inspire us to innovate in our classrooms, and strengthen our commitment to nurturing competent, responsible, and future-ready graduates. I also take this opportunity to acknowledge the efforts of organizing committee, the coordinators, especially Dr. P.S. Abhita and Dr. T.L. Anusha, and supporting staff whose dedication and hard work have made this program possible. To all participants, I urge you to actively engage in sessions, interact with the experts, and make the most of this learning opportunity. Let us use this FDP as a platform for collaboration, knowledge sharing, and professional growth. With these words, I once again extend a warm welcome to each of you. Thank you. Thank you, madam.
Thank you, sir. We sincerely thank our principal, Dr. C. Sudhakar, for your inspiring inaugural address. Your encouraging words have truly set the tone for this faculty development program and will certainly motivate us to make the best use of this opportunity. Thank you, sir.
Thank you.
Now, I request Mrs. Srija, Assistant Professor, of CSC department to give us an overview of our institution, its journey, achievements, and all the facilities it offers.
Good evening, everyone. Ma'am, am I audible?
Yes, ma'am, you are audible.
Yes. Good evening, everyone. Myself, Mrs. Shrija, Assistant Professor, Department of Computer Science and Engineering. I'm excited to introduce you to our vibrant college. Marthandam College of Engineering and Technology, MACET, is situated in a hamlet called Kuttakuli, Kanyakumari district, Tamil Nadu. It is located midway between Trivandrum and Nagarjuil. MACET is the fruit of dedicated efforts of the members of Marthandam Educational and Charitable Trust, MACT, established in the year 2006. MACET has been initiated to advance the well-being of the people through the creation and dissemination of technical knowledge. Organized with the primary objective of providing quality technical education to the bright children from rural areas. Marthandam College of Engineering and Technology is a student-centered institution with good learning and teaching environment. MACET has a state-of-the-art facilities and highly motivated team of faculty members. MACET is approved by AACT and affiliated to Anna University and ISO 9001 and 2015 certified institution and NAC accredited institution. So we offered the undergraduate degree programs, be civil engineering, be mechanical engineering, be electrical and electronics engineering, be electronics and communication engineering, be computer science and engineering, BTech information technology, BTech artificial intelligence and data science. Also, we offered a postgraduate degree programs, ME computer science engineering, ME power electronics and drives, ME VLSI design, and MPA, and finally MCA. So with that, I'm going to conclude about our uh, overview of our institution. Thank you all. Have a great day. Thank you, ma'am.
Thank you, ma'am. Every institution is defined by its vision, achievements, and the people who contribute to its growth. I thank Mrs. Srija for sharing our college's incredible profile. Thank you, ma'am. Every program begins with a clear vision and well defined objectives. To enlighten us on the aims and expected outcomes of the faculty development program, I'm pleased to invite our coordinator of this FTP, Dr. P.S. Abida, Assistant Professor of Physics Department, to address the gathering.
Good evening to all. Ma'am, am I audible?
Yes, ma'am, you can continue.
Okay, good evening to all. I am Abida, Department of Physics, Marthandam College of Engineering and Technology, R2. I am here to share the objectives and outcomes of the Faculty Development Program. The objective of advanced materials, rare earth and critical minerals is to ensure the sustainable development, innovation and strategic use of essential materials that are key to modern technologies and clean energy. To develop and deploy materials with superior properties such as strength, lightweight, durability, conductivity, and thermal resistance, to enhance performance, energy efficiency, and sustainability across industries, to secure a reliable and sustainable supply of rare earth elements critical of high-tech and clean energy applications, to ensure secure and managed mineral essential to the economy and emerging technologies. Outcomes: development of cutting-edge materials for sector like aerospace, defense, healthcare, and electronics, improved product performance, durability, and efficiency, increased availability of critical materials for solar panels, wind turbines, and hydrogen fuel cells, development of secure and transparent supply chains for critical materials, reduced dependency on foreign sources for rare earth and critical minerals, development of next generation materials such as nanomaterials, smart materials, biomaterials, etc., support for emerging sectors such as semiconductors, space tech, and electrical mobility. Hope this session will be very useful for us. Have a great day. Thank you.
Thank you, ma'am. I sincerely thank Dr. P.S. Abhita for outlining the objective and outcomes of the FTP in such a precise and meaningful way. Thank you, ma'am. Now, as we come towards the close of the inaugural session, it is time to express our gratitude to all the dignitaries and gathering. It is my honor and privilege to deliver the vote of thanks on this special occasion of this faculty development program inauguration. First and foremost, I express my heartfelt gratitude to our chairman, Engineer F. Prince Vino, Dr. C. Sudhakar, for their constant support and encouragement with their gracious presence. Thank you, sir. I would like to thank the coordinator, Dr. P.S. Abhita, and all the staff members for their helping mentality and support for making this event possible. And I would like to thank all the participants for making this event a possible and meaningful way. Thank you all. So within a minute, our chief guest will join. So please kindly wait. Now, I'm delighted to introduce our session speaker, Dr. A. Pandikumar, Senior Scientist, CSIR, Central Electrochemical Research Institute, Karaikudi, India. Dr. A. Pandikumar is currently working as Principal Scientist in CSIR, Central Electrochemical Research Institute, Karaikudi, India. He obtained his PhD in chemistry from the Madurai Kamaraj University, Madurai. He successfully completed his postdoctoral fellowship at the University of Malaysia under a high impact research grant. He in the top 2% of scientists list in the world database released by Stanford University, US 2024. Moreover, he is recognized as the world top 2% scientist in the single year category and also in the career achievement category. He has continuously achieved this record for the last 5 years. Further, he is awarded RSC Upgrade Member by Royal Society of Chemistry UK 2021. Recently, he has received the prestigious Young Scientist Award for 2023 Saraswati Srinivasan Prize from the Academy of Sciences, Chennai, Tamil Nadu, for his pioneer contribution to solar energy conversion. Recently, he has been elected as Fellow of the Academy of Sciences, Chennai, Tamil Nadu. He is a life member Society for Advancement for Electrochemical Science and Technology. His current research involves the development of novel functional materials for photocatalysis, photoelectrocatalysis, composite solar cells, and office applications. He that appeared in more than 160 peer-reviewed journals, including 14 review articles, and also have 9,700 citations with a H-index of 61. He secured funded project worth of 5 crores from DST, CSIR, SEB, etc. Currently, he has completed 4 PhD candidates and 6 is going on. So on the another side, he served as a guest editor for a special issue in the Materials Focus journal, Applied Surface Science, Advances, and edited 21 books. It is my privilege to invite our esteemed resource person, Dr. A. Pandikumar, Senior Scientist, CSAR, Central Electrochemical Research Institute, Karaikudi, who has made remarkable contribution to the science society. We are truly honored to have you with us today. Now, I feel honored to call upon our respected speaker, Dr. A. Pandikumar, to kindly take over the session and share his valuable insights with us.
Thank you, madam. Am I audible?
Yes, sir, you are audible.
Yes. Okay. Good evening to all. So I have chosen the topic photoelectrocatalytic water splitting, a journey from lab scale to prototype. So why I have chosen this particular topic, so now Indian government conducting the National Green Hydrogen Mission. So in that mission, they have 20,000 crores they have allocated for this activity, especially for India to become a global hub for green hydrogen production and the export. So that is the prime objective of this India's national green hydrogen mission. So in that way, if you look at this, what are the methods available for the hydrogen production is very expensive, as well as it require high electricity and other things. So here I am proposing that the methodology, by using the sunlight, we can generate green hydrogen. So these kind of activities that can be done at the lab scale. So in the lab scale investigation, it's end up with the publications. So mere publication, but it will not give any further development. So in this way, we are just pushing from lab scale to prototype development. So for that, I have chosen this topic. Okay, so before moving to my lecture, I just want to give small introduction about my institute. So I am from CSAR Central Electrochemical Research Institute. So this institute is established to mark the occasion of our independence. So when Pandit Jawaharlal Nehru, he wanted India become a self-reliant country. For that, he want to establish several national laboratory after getting the independence. So that time, Lalapa Chettiar, he approached Pandit Jawaharlal Nehru. He offered 50 lakhs rupees and 300 acres land to establish this Central Electrochemical Research Institute at the remote place of Karaikudi. So this is our 11th national laboratory. So our institute offer a final year project for a BTech and the MSc MPhil student. So the people can work with the scientist for their final year project. And also we are having sophisticated analytical instrument facility for research scholars as well as faculties. In addition, we are offering the PhD program that will come under ACS here, and the BTech program, Chemical and Electrochemical Engineering, it comes under Anna University. So this picture is taken during the foundation day. This picture is taken during the inauguration of CSCR Sikri. So this is our main entrance. So our institute mandate is the electrochemistry. So we are providing solution for all industrial problem with the help of electrochemistry. So based on that, our activity categorized into 6 types. So corrosion and material protection, electroplating and metal finishing, electrochemical power sources, electroorganic and materials electrochemistry, electrochemical process engineering, electronics and the electrocatalysis. So these are the different type of our activity, especially this corrosion and materials protection. They are mainly working for the material protection. So if you visit a Bombay Bridge, the Bombay Bridge maintenance undertaken by CSCR Sikri. Likewise, if we visit Tungabhadra Dam and many dams that also undertaken by our CSCR Sikri. Then the electroplating and metal finishing division, they are mainly working for bioimplants. So the bioimplant material as well as the strategic sector, especially the thermal barrier coating for a rocket with the ISRO. Then trivalent coating, trivalent chromium coating for gun barrels, that is with the DRDO. So these kind of activities they are doing with the electrochemistry. Then electrochemical power source division, they are offering many energy conversion and the storage devices like fuel cells, batteries. Basically, battery means lithium-ion battery, sodium-ion battery, metal-air battery, zinc bromine battery, redox flow battery. So this kind of batteries. Then supercapacitors, they are also working on supercapacitors, as well as the solar cells, dye solar cell, then perovskite solar cell. These kind of activities also they are doing. Then electroorganic and materials electrochemistry division. So they are developing several materials for energy electrochemical applications, as well as they are doing electroorganic synthesis for active pharmaceutical ingredients. Then the electrochemical process engineering, they are mainly working for hydrogen production as well as carbon dioxide capture and utilization. So this electronics and electrocatalysis division, they are mainly working for the healthcare monitoring. So they are developing several biosensors for uh, several disease monitoring. So these are the our institute overall activity. So in this institute, I am leading that the solar energy materials research group. So my group is mainly working in dye solar cell, perovskite solar cell, then electrolyzer for green hydrogen production, photoelectrochemical cells, hydrovoltaic devices. So these are the reasons, some of the recent development in our research group. So this is my research team. So this picture is taken just June month. Then these are all some of the distinguished honorees, those who are completed the tenure and moved to the next position. So now let me come to the story. So why our government want to announce a national green hydrogen mission? So in the year 2016, there is a conference held in Paris. So there 195 countries prime ministers, they have participated in the conference. Then they have seriously discussed about several issues, and then finally they have concluded that the climate change mitigation, that is the important is utmost essential, because if we are unable to predict the climate means it will subject to that several natural disaster will happen. So they have finally agreed and signed the agreement, and the agreement entered into the force on 4th November 2016. So this agreement covers climate change mitigation, adaptation, and financing for the related activities. So once our Prime Minister back to India, he announced the National E-Mobility Mission. So in that E-Mobility Mission, switching from the fossil fuel based vehicle to fossil fuel based vehicle to e-vehicle. So that means so the e-vehicle is nothing but it is called a plug-in type electric vehicle. So this plug-in type electric vehicle, it contains battery pack, battery management system, high voltage cables, and specially designed motor and power electronics. So as like a charging our mobile phone, you can plug in and you can charge it. Okay, so this is called plug-in type electric vehicle. So you just to look at this, this is the survey taken between January to December 2020. So even it is a pandemic period. So almost 16 lakhs e-vehicles are sold out. So it seems the e-vehicle is a very expensive. Uh, so alternatively, the people are moving to e-scooter. So this is a survey is taken between January to December 2021. So almost 1,35,000 e-scooters are sold out. So it seems like higher class people as well as middle class people both are having awareness on switching from the fossil fuel based mobility to e-mobility that will make that that will be a green vehicle. It will not pollute the environment. So this is what the middle class people also moving towards e-scooters. Then government also setting policy for each state. So they want to register at least 5 lakhs e-vehicle in 5 years, and they are giving tax rebate and exemption from the interest if we get a bank loan. So likewise, several attractive schemes they are announcing, since the government is believe that this e-vehicle is a green vehicle. But in reality situation, it is a e-vehicle. It is charging from the charging station, but the charge is generated from the diesel generator. So it seems that even this fellow, it is indirectly pollute the environment. So then how we can make a perfect mobility? So that is the key question. So it seems like a first option, you just look at this, these are all the fossil fuels, so it will go into exhaust soon. But when we talk about the other renewable energy source, wind have the potential to meet our energy demand. So but the problem, it is wind is a seasonal and regional. Why? Because wherever the wind flow is good, there only you can install it. Then and also you cannot get the wind throughout the year. So that is the another problem. Okay, so in this case, you have to consider solar. So India is a sunlight abundant country, so you can make use of solar. Then the other option is a hydrogen. The hydrogen is an alternative to fossil fuel. It has a high energy density, 140 megajoules per kilogram. It is a clean fuel. It will not pollute the environment. So once it is consumed in fuel cell, it produces only water as a byproduct. So it has that advantage, like several advantage, high energy conversion efficiencies. It is easily produced from water without any emission. It is hydrogen is a earth abundant, so you can easily store in a different form, like gaseous form, liquid form, or solid form. So this will be used for long distance transportation also. So these are all the merits of hydrogen. Now let me know the color code for hydrogen, because based on the production method, the hydrogen having different color codes. So normally we can use the renewable energy source for producing the hydrogen. This is one of the source. Or nuclear energy, it is another source. Then natural gas, this is another source, and coal is another source. So normally the hydrogen is produced by electrolysis method, steam methane reforming, and the coal gasification process. During the coal gasification process, it will emit the CO2 and it produce hydrogen. This kind of hydrogen is called black hydrogen or brown hydrogen. Uh, Suppose the emitted carbon dioxide captured and is and stored in CO2. It's like it's called a blue hydrogen. Suppose in the steam methane reforming method, if it is go out means, then it is called the gray hydrogen. Suppose if you are using the nuclear power, you are creating nuclear waste, it is a pink hydrogen. Suppose if you are using renewable energy, it will release oxygen, then it is called the green hydrogen. So these are the color code for hydrogen. So you just look at this. This is a picture. This also e-vehicle. So this is the train running in Germany. This is fuel cell Toyota Mirai car running in Japan. So it is a zero emission bus. It's running in United States of America, and this is the Hyundai truck. So it is for logistic purpose. So I will just explain how this fuel cell vehicle is work and how it is become EV. So you just look at this. This is the cross-sectional image of this particular car. So here you are having that battery, then hydrogen storage tank, and fuel cell stack, boost converter, power control unit, specially designed motor, and a specific membrane that will allow only oxygen from the environment. Okay, so once you ignite the vehicle, what happened? The hydrogen from the hydrogen storage tank, it reaches the fuel cell one side, oxygen from the environment that will reaches the other side. So both will combine together in the fuel cell stack. It will produce electricity. That electricity is used to drive this vehicle. The byproduct will be here is the water. So you just look at this. This is the uh, working principle of this fuel cell. So this is what. So once the hydrogen is reaches to that electrode surface and it converted into proton and release the electron. This electron is collected as electricity, and this proton is combined with this oxygen. So finally it released water. Okay, so this is what it's working. So when we talk about the mileage of this particular this one, you can fill maximum 5 kg of hydrogen. So you can drive up to 500 kilometers. So that means per kg hydrogen, it's like 100 kilometers you can drive. So I will just show a small video for your better understanding of the working principle of this fuel cell vehicle. Is my videos visible?
Yes, sir. Sir, visible.
Toyota. Always a better way.
Now you may clear on working principle of this fuel cell vehicle, right? So here we are giving the feedstock as a hydrogen. Then it combination with the oxygen, it produce water and electricity. So the water is the byproduct. So this is the advantage of this particular system. Again, as compared with the plug-in type EV vehicle, suppose you want to charge the vehicle, you have to wait for 2 to 3 hours so that you can drive 400 kilometers. But when we talk about this fuel cell vehicle, as like a filling a petrol, you can just wait for 3 to 5 minutes. You can fill a 5 kg of hydrogen. Okay, so that is the merit over here. But when not we are talking about the positive of positive side, we have to consider the negative side. Why? Because hydrogen is highly explosive. So this is the Toyota Mirai car. It had an accident. So suddenly the hydrogen storage tank got exploded, then immediately it catches fire. So this is the one incident. Then another incident, it is improper handling of hydrogen. There is a hydrogen filling station exploded in Norway. So this is the another incident. So then, while considering the safety aspect, so the Hyundai truck, sorry, the Hyundai company, they have developed yeah, excellent hydrogen storage tank. So by introducing layer by layer structure, that is a high density polymer, plastic, carbon fiber composite, glass fiber composite, polymer foam, then flame resistant composite material that is coated over the surface. So finally it will be used for storing the hydrogen in this particular car. They have done crash test. So this time the car got a physical damage, but the hydrogen storage tank, it doesn't get exploded. Okay, so we have to think about the hydrogen storage aspect also. So that is the important thing. So that is life threatening also. Okay. So you may ask that, sir, if any technology is available in the market in abroad, so it will take at least 1 decade to reach us. So when we will have that these kind of fuel cell vehicles will run in our country. So for that answer, our CSCR SICRI in collaboration with our sister concern lab, so we have developed a fuel cell, and it is tested and assembled, and we are introduced the zero emission fuel cell bus, and this technology is transferred to the Sentinel lab. So so this video is taken during the inaugural launch of this zero emission fuel cell bus that is developed with the CSA SICRI technology. So shifting gear towards green mobility. Okay, then later stage last year, our the Tata Motors, they got this technology. Then they have developed 20 number of buses, and it is dedicated to IOCL, Indian Oil Corporation employees at Ghaziabad. So they are going to use this fuel cell bus for a shuttle service. Why? Because this is the primary idea for dedicated that to 20 buses, rather than the employees are coming to too many vehicles. They can give free shuttle bus, so they can reduce that fuel usage and the environmental pollution, as well as reducing the traffic charge, as well as the saving the parking space. So that is the idea. Okay, so that's why they have done this one. So previously they also dedicated 5 buses, hydrogen fuel cell buses. So in the year 2018 19, but that fuel cell bus, that can be run with any kind of hydrogen. That hydrogen can be produced in any different sources. But this particular hydrogen, this is India's first green hydrogen fuel cell bus. So it seems this will only use that green hydrogen. No other hydrogen, they won't use it here. So this is the one. So now we have completed in the road. So next, water. So here, if we visit that Cochin, so Cochin, the Asia's first marine metro, that is located in Cochin only. So previously the catamaran, that is the marine metro, that is operated with the help of battery. So that is the plug-in type electric vehicle they have used. But last year, 2024 February 28th, our Honorable Prime Minister flag up the hydrogen fuel cell powered passengers catamaran. Okay, so this is also our CSR technology. So in collaboration with the INCL. So now we have moved to the water. So the next our focus on track. So in another 2 to 3 years, you can see that this one. What is that? The hydrogen powered train also you can see in the track. So that is that our ultimate target in the next 2 to 3 years. So this is what. So now this hydrogen will be used for the e-vehicle. So suppose this hydrogen is not only for used in e-vehicle, it can be used for the modified engine, internal combustion engine modified vehicle also. They can use this hydrogen, so they can run without any pollution. So for that, last year my student was attending a conference which is organized by 5 different ministry. So engine, and they have showcased the vehicle for public. So my student went and see that. After that, she told me. Then I just browsed on that particular development. Then I come to know that. So the hydrogen can be used for non-e vehicle also possible. So I just saw that the another video about that the non e vehicle based the hydrogen mobility.
On the road that leads to the dream of greener mobility, the world now gets a new set of wheels to steer that journey towards reality. Presenting Ashok Leyland's pioneering technology, the hydrogen internal combustion engine vehicle that's built on the Avatar modular platform. The fuel delivery system on this vehicle is modified to use green hydrogen instead of diesel. A strong carbon fiber composite cylinder ensures safe storage and high pressure endurance of up to 350 bar. That's extremely easy to install, lightweight, and maintenance free. With minor changes to our H series 6-cylinder internal combustion engine, we are able to deliver power and torque equivalent to a conventional engine. With a lean combustion strategy, it ensures minimal emissions and less noise, resulting in an efficient, cleaner, and a quiet drive. The hydrogen internal combustion engine vehicle delivers the highest payload and long range. Its aggregates are similar to a diesel vehicle, aiding easier maintenance, all while complementing the hydrogen mission that supports the Atmanirbhar Bharat initiative. These benefits make hydrogen internal combustion engine vehicles a perfect vehicle to drive us towards the future. Ashok Leyland, कोई मंजिल दूर नहीं.
So this is the technology in the area of recent development in the transport sector. So now if hydrogen powered vehicles are come to the market, then we have to see that how much the hydrogen demand will be going to happen. So we are in the middle of the 2020 and 2030. So now the hydrogen demand per annum 70 million metric ton. So in the year 2030, it is expected that to reach 100 million metric ton hydrogen per annum it's record. So why? Because there are few new color codes are appear here. So in the year 2050, where we are going to achieve the net zero carbon emission goal, so we need almost 540 million metric ton of hydrogen for different sector, especially the power generation sector. So in this case, now itself we have to see that what is the technology is available for the green hydrogen production. So that is almost urgent. So in CSR system, if any technology that will be measured with technical readiness level scale. So first I will explain what is that the technical readiness level scale. So here you may see this number TRL1 to 9. So it seems the number itself it will shows that how progress in the research and where the research is standing. So this is what, for example, TRL 1 to 3. So for example, a boy demonstrating something in a science exhibition. So he may take some battery, then connected with the wire, then he put it into the water, then he may see the bubbles. Means it's a basic concept. So it's like a TRL1. The same thing if you're a person doing project and submitting as a thesis, so that is TRL2. If a person is doing experiment and managed to publish a paper, so these are all the TRL level 3. So these are all basic levels, especially the academia, then the key knowledge development. These are all. So suppose I am doing a synthesis of some material. So I can do it in a milligram scale. So whether if I am able to scaling up the same material in a kilogram scale or a gram scale, then that will be moved ahead from TRL3 to TRL4. So that is called TRL4. Then if we are able to developing this technology in collaboration with some industry or something, then it is a TRL5. So then if you are technology demonstrated in the industry, then it is a TRL6. Suppose you have worked for like how much the expense is required to sell 1 kilogram of hydrogen. So that will work out manpower cost, land cost, building cost, electricity, tax, uh, machinery cost, then interest, all will put together. Then finally you will arrive some numbers. So the once that number is comes, then it will go for market. So such kind of system development, it is in the applied level. That is business development. So this is what we call it as a TRL7 to TRL9. So now let we see the technologies TRL level. So the blue hydrogen and the gray hydrogen, these hydrogen production method, it's already matured state. So this hydrogen is only available in the market. So now the alkaline electrolysis process and the polymer electromembrane biomass gasification. So these are all just to attain the mature state. So this is in the middle of the way. The it's in many patterns are these things. Then when we talk about sunlight to hydrogen production, so still it is in the infant stage. That means somebody preparing the material, then they are exploring the hydrogen production in the presence of sunlight. Then they are able to publish a paper or something. So that's why they are still lacking with the TRL level. So further we have to push this one to TRL4 or TRL5. So this is what our ultimate aim. So now you know that the technology available for the green hydrogen production. So there is no defined methods is available for green hydrogen production in India. So that's why our government announced the National Green Hydrogen Mission. So the objective of this mission to make India a global hub for green hydrogen production and export. So this is certain. So for that, initially they have allocated 800 crore budget. Then after know the importance of this particular green hydrogen production, our Union Cabinet approved 20,000 crores for this particular research area and development. So these are all the expected deliverables by 2030. That means we have to increase that the green hydrogen capacity 5 million metric ton per annum. Then we have to increase that the electrolyzer capacity up to 100 gigawatt. Then, as already mentioned, that the green hydrogen production that will be powered by renewable energy source. So, what are the renewable energy is produced? The rest of the electricity that will be connected to the grid. In that way, the renewable capacity 125 gigawatt we can increase it. Okay, so these are all direct benefit. So indirect benefit, we can save 1 lakh crore rupees in the way of stopping the import of crude oil. So this is a one indirect benefit. Then if we start using hydrogen vehicles, then we can mitigate 50 million metric ton of hydrogen per annum. That also uh, possible. Then 6 lakhs job opportunities we can create, and 8 lakhs crores corporate investment that will be happening in India. So for the last two cases, I will give one typical example. There is a company. There is one company, Omium. So that is a US based company. So that have two plants for green hydrogen production, one in Sengalpattu, another one in Bangalore. Okay. So last year our chief minister visited the United States of America. Then he signed the agreement with the Omium company to set up a new factory in Sengalpattu. So for that, they have going to invest 400 crores. So which has that capability of producing 500 job opportunities. So this is what one typical example. So so likewise, many has to come to India. So this is the picture is taken during that the signing of agreement. Okay, so he is Chokkalingam. So Chokkalingam, he is the chief technical and scientific officer for the particular company. So he is our alumni of our institute. So he completed his undergraduate BTech in chemical and electrochemical engineering. Then later he completed his PhD from US. Then he joined in this company and worked for 15 years. Now he become a chief technical and scientific officer. Okay, so now let me come to the original story. So how we can produce that the hydrogen from the sunlight? You just take a semiconductor, put it into the water, then expose to the sunlight, then it will produce hydrogen and oxygen. So the simple equation involves hydrogen and oxygen evolution reaction, two reactions. So the one is two proton, two electron, another one is four proton and four electron. So this involvement of this four proton, four electron, it called as a rate determining step. And also you just look at this overall, you want to split the water, you need 1.23 volt by theoretically. So how this water splitting takes place at the semiconductor surface. So this is the semiconductor, it has valence band and the conduction band. So upon illumination with light, the valence band electron is promoted to conduction band and it oxidizes the water, and the conduction band electron it reduce the proton and it produce that hydrogen. But in this case you will get a mixed state of the hydrogen and oxygen. Okay, but when we go with the photoelectrochemical water splitting, so these are the types of photoelectrochemical cells. So one is a photoanode. So the n type electrodes that is always called as a photoanode. So the p type semiconductor, when we use it, is called as a photocathode. So if you have both, you can form a tandem cell. So these are the different type of photoelectrochemical cell. So in this photoelectrochemical cell, was developed by Honda and Fujishima in the year of 1972. So they have developed this photoelectrochemical cell, which consists of two compartments. That will be both the compartment that has the anode and the cathode. So both will be connected through the circuit, and upon elimination, what will happen? It's oxidize the water, and it release that oxygen and the proton, and the proton is moving towards the proton exchange membrane, and they accept the electron here, and it reduces to form a hydrogen. So here you can separately collect that hydrogen and oxygen. So you want to start your career in photoelectrocatalyst water splitting. You have to consider these 4 points. One is suitable optical property, another one is suitable bandage alignment. So the other one is charge separation and transport, and stability against light radiation. So these are the important aspect you have to consider for the making that photoelectrochemical water splitting. So uh, we are having that several materials that will be used for water splitting application. So especially our interest bismuth based material. Why? Because it has four different component. One is single component, binary, and ternary, and layered structures. So why our interest on bismuth based material? Because when we look at this valence band position seriously, so the valence band positions of bismuth based materials are more positive than the oxygen evolution potential. So as already mentioned that the oxygen evolution potential is that rate determining step. So this if we make that the oxygen evolution reaction kinetics more facile, then we can enhance the hydrogen production rate. So this is what our interest. But whenever we are taking that the simple semiconductor, it suffers from charge recombination process and poor charge transfer property. To overcome this limitation, people can adopt component adjustment, surface modification, morphology control, heterojunction formation. Okay, so our approach is the formation of heterojunction. Why? Because you just look at this picture, a person is jumping from the ground. Then after that, again he is reaching the ground due to that earth gravity. Likewise, if you take single semiconductor, upon elimination, it will undergo charge transfer process. But due to that Coulombic force, it will undergo charge recombination force. So the electron and holes will be recombined together. Finally, the net result will be zero. So you look at this particular picture. So here, the person putting that to table, then he is jumping and standing on the table. He is now spatially separated from the gravity. So likewise, if we add another semiconductor here, it is spatially separated. Okay, so again, this heterojunction, it's having three different types. So one is straddling gap heterojunction, another one is staggered gap type 2 heterojunction, then broken gap heterojunction. So here in the type 1 heterojunction, both oxidation and reduction will take place in the secondary semiconductor. But when we talk about the this type 2 heterojunction, the electrons reduction and oxidation will be takes place in the opposite direction. So this is predicted one, so it will not used for any application purpose. Okay, so here you want to here the type 2, the electron will be step up and holes will be step up. Sorry, electron will be step down, holes will be step up. But here both the electron and the holes will be step up. So other than that, if we have that p-type semiconductor, n-type semiconductor, we can combine together, we can form a p-n heterojunction. So while combining together at the interface of both the material, there is an internal electric field is developed in the space charge region. So here the electrons will be moved towards the n-type semiconductor, holes will be moved towards the p-type semiconductor. So this is also behave like a type 2 semiconductor. Then jet scheme heterojunction. So the jet scheme heterojunction. So normally you will any reactions, the electron will be stepped down. But if some case you want to step up the reaction, step up the electron. So you can use this eject scheme mechanism, heterojunction. So here you can add a mediator. So the electron will be moved from here to here, and here to mediator, mediator to holes, and holes to conduction band. So this is the mediator based one. Suppose you don't want to mediator, then it is closer to the conduction valence band. Then the electron will be directly move here. Then from that it will move here. So it is a mediator free eject scheme mechanism. Okay. So you just look at this. There is a plenty of catalysts that will be used for photoelectrocatalytic water splitting that will fulfill the. So it's like metal oxides, metal nitrides, metal chalcogenates. Other than that, there is a polymeric carbon nitride that is a metal-free semiconductor that also can use. So you can use any kind of heterojunction. So I will give one example for the heterojunction, PN heterojunction that is developed in the lab scale. So this is one example. So here we have done bismuth vinaigrette and copper oxide heterojunction for photoelectrocatalytic water splitting. So for that, initially we have done electrodeposition of the bismuth-based material. Then followed by it will subject to the electrodeposition with the copper acetate in acidic acid. Followed by calcination, it forms the bismuth vinaigrette and the copper oxide heterojunction. So you just look at this. This is the reference pattern of the FTO. This is after deposition of the bismuth vinaigrette. So here you can see that the signature peaks due to that the bismuth vinaigrette. Then addition after incorporation of this copper oxide, further the introduction of additional peak for the copper oxide that will source from the diffraction pattern. So it clearly reveals that the heterojunction formed between the two interfaces of material. Then this is the FECM analysis. So this is bismuth vanadate electrode. This is after electrode deposition of copper oxide over the bismuth vanadate electrode. So you just look at this. This is the elemental mapping due to that presence of bismuth, vanadium, oxygen, and the copper in the electrode. So this clearly confirms that free from the impurity. So this XPS analysis shows that the before and after making the heterojunction, so there is a shifting in the binding energy for both the core levels. So that is revealed that the successful formation of heterojunction between the two interfaces. Then after forming the heterojunction, the visible light absorption got enhanced. Okay, so we have calculated the band gap by using the Tox plot method for bismuth vinaigrette and copper oxide like 2.5 electron volt and 1.47 electron volt. Then we have studied the photoelectrochemical performance in the dark and in light condition. So in the absence of light, there is a poor response in the current. So once it is exposed to the sunlight, what happened? The photo current got increased. So after forming the heterojunction, so there is a further one-fold enhancement in the photocurrent. Then we have checked that the charge separation capacity. So for that we have choked the illumination and recorded this particular linear pole tomogram. So the rise and the fall in the photocurrent is highly stable and reproducible. Then we have also studied the surface charge transfer efficiency by using the sacrificial agent, and it is found that the for a pristine material that shows 25%, and the heterojunction material it shows that 41.5%. Then we want to predict the charge transfer mechanism. For that, we have done the XPS UPS analysis to know the valence band maximum position. So we have calculated the valence band maximum position, and we have measured the Fermi level by using the Marx-Katsky analysis. Then we have adapted the values in the following formulas. Then finally we have arrived at this kind of the energy level position for the both semiconductor. This is before contact, this is after making contact. So it create internal electric field at this space charge region. Then it will subject to that illumination with water. Then it will be oxidize the water into oxygen and proton. That proton will accept the electron in the cathode chamber. Then finally it will produce the hydrogen. So this is water. So the stability also we have checked. It shows that good material stability. The durability also it can able to constantly produce that hydrogen. Then the efficiency we have calculated. It is almost closer to the benchmark value 0.3 percentage. So we have done several work with the powder in photoelectrocatalyst. So especially the powder-based system that is produced through the hydrothermal method. Then the thin film approach for making the device. So we have compared the performance for the hydrogen production rate and the efficiency of the system. So in the powder processed method, it shows poor hydrogen production rate and poor efficiency. But once we make it as a thin film form, so it shows that the high hydrogen production rate. So then we have taken this thin film approach for making the prototype device. So what are the result I have discussed here until last slide, that is comes under TRL3. So I just want to go beyond the TRL3. So for that, the best performing electrode is a bismuth vanadate electrode. So for that, I have done the electrode deposition by scaling up from starting from lab scale 1 centimeter square to 25 centimeter square. So what are the result you have seen in the previous slides and all, that will be done with this 1 centimeter square electrode. So now we have scaled up the electrode from 1 centimeter square to 25 centimeter square. Then we have developed this prototype photoelectrochemical cell. So it is made with the quartz window and acrylic material. Then we are using the Nafion membrane for the proton exchange membrane. Then we have performed that photoelectrochemical water splitting. So here, when we increase the area, the photocurrent got increased. But I just want to see whether this 1 centimeter square is behave like a 25 centimeter square. For that, I have converted into current density. So now the trend will be reverse. So here the efficiency also decrease as the areas increase due to that high charge recombination process and the charge transfer resistance. So then I just saw this picture on the Facebook. Then I have modified my electrode fabrication method into line pattern and grid pattern. So this is what we have modified this electrode fabrication method. Then we have compared to that the efficiency loss. It start from 20 to 50 percentage loss in the prototype device. So for that we have modified the electrodes by making line pattern and grid pattern. Then we have tested the performance. So here it seems like we have reduced the efficiency loss from 51 percentage to 27.6 percentage. Further, we have added the sacrificial agent. Then we are reduced it to below 20 degrees, 20 percentage. Then we have checked that the hydrogen production rate. So we are able to get to 227 micromoles per kilogram per centimeter square. The stability also it shows that excellent. So this is what we have developed. So this is the overall summary of the presentation. So initially we have discussed about the importance of the hydrogen production, then the photoelectrochemical cells for the hydrogen production and its type, and the materials that will be used for photoelectrochemical water splitting, and the types of heterojunctions, and some of the materials developed in my lab and its performance for the hydrogen production that also discussed. Finally, I have shown that the prototype device development and its performance. So for this particular prototype development and beyond the lab scale device development. For that, my student got best PhD thesis award from the ACS here. These are the publications related to the journey from the lab scale to prototype development. This is a edited book which will shows that the fundamentals information about the heterojunctions in material aspect. So I have recognized for the contribution of this solar energy conversion that is recognized by Academy of Science and offered me the Young Scientist Award 2023. So, as already mentioned, that my student went for the conference organized by 5 different ministries. So she participated there, and she has been bagged 20,000 rupees cash prize with the citation for green hydrogen production. And another recognition from our group, Ms. Rajalakshmi. Uh, she was awarded for the travel grant, as well as he participated in the 74th Lindai Nobel Art meeting last month for her outstanding contribution in the green hydrogen production. So the picture is taken during the participation in the meeting. So finally, the acknowledgement part. So I would like to thank our institute director and head of the department for their constant support and encouragement in the area of green hydrogen production, and the staffs from CA for the analytical characterization, and the funding agencies for providing necessary facilities, especially the output that comes from the DSTHFC hydrogen and fuel cell and CACR first. So this is the take-home message. We have to switch into the e-mobility that is powered by fuel cell. So for that, the produced hydrogen that is through the green hydrogen method. Thank you for your kind attention.
Thank you, sir. Now the session is open for question and answer session. Please, all the participants can ask your questions now.
If you have any queries, you can post in the chat box also. I can read and answer it.
Sir,
Yes, sir.
yeah. As you mentioned that three different conventional heterojunctions like straddling, staggered, and a broken type.
Yes, sir.
Which one is best?
Type two heterojunction, sir. Type two
Type?
heterojunction. Why? Because the oxidation and reduction will be take place in the opposite direction. So the
Okay.
electron and the holes will be spatially separated. So there, the possibility for the recombination is very, 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 very less.
Okay. And one more question. How do you make a grid, sir, in your large area coating of that material?
Actually, before electrode deposition, first we will draw the line. Uh,
Oh,
we will draw the line by using the OHP marker. Then later we will mask with the Teflon tape. That
okay.
particular area we will mask with the Teflon tape. Then we will do the electrode deposition. After the electrode deposition, we will remove the Teflon tape. Then we will just add print the silver ink. Then
Okay.
after printing the silver ink, then we will mask with the epoxy, because the
Okay.
silver is readily form a silver oxide. Then it become a semiconductor. Then again it's a problem. So we will just mask the silver with the epoxy. So then we performed the experiments.
Okay. Thank you, sir.
Participants, is there any other questions? You can ask now.
Good evening, sir.
Good evening.
Yeah, sir, very nice and useful session. I heard. Yeah, very nice, sir. Even I am working also in this field, the hydrogen production,
Mm-mm.
not the photocatalytic, rather electrocatalytic. So
Okay.
just I want to know one thing that you told that hydrogen production, there are several how to say this. You showed that trial something that level 1, 2, 3, 4, 5, 6.
TRL level, TRL levels.
TRL level, yes, TRL level. So there it was mentioned that alkaline fuel cell, this is already matured, right?
Yeah, it is a matured. It is a matured. Alkaline water
Matured.
electrolysis is
Yeah,
matured.
that is matured, but people are working on that, and they are trying to develop hydrogen production by using alkaline fuel cells. So what else can be developed? Means what is left?
Actually, we have to develop a PEM-based system, proton exchange membrane-based electrolyzer.
Yes, sir.
So that will be beneficial for making high hydrogen production rate. So the company I have shown in one slide, Omium company. So
Yes, sir. Yes, sir.
they are doing a huge amount of hydrogen production by using the proton exchange membrane. But when we talk about alkaline exchange membrane, the membrane cost is very expensive as compared with the proton exchange membrane.
So, sir, just one last thing, just my curiosity, that
Hmm.
if I want to develop usable things, commercial things, so in your opinion, that PM will be much more advantageous than alkaline fuel
Yes,
cell.
yes, yes, sir. Yes, sir.
Okay, sir. Thank you very much, sir. Thank you.
Thank you, sir. Hmm.
Sir, another one person have asked a question in chat box. Can you answer to that, sir?
Yeah, I'll check it, ma'am. Why do researchers choose bismuth vanadium oxide or any other materials? So actually, the hematite you can choose. That is also is good, but the probability for rusting of hematite is more. But the bismuth vanadate it fulfill the four criteria as I already mentioned in the one slide. It should have the visible light absorption, should have that suitable bandage alignment for hydrogen and oxygen evolution potential, and it should have that high charge separation and migration property. So that also it has, and it has that high stability. So that's why people are choosing the bismuth based materials.
Participants, any other questions? So we'll wind up the session. Thank you, sir. On behalf of our institution, Marthandam College of Engineering and Technology, I extend a heartfelt gratitude to our esteemed resource person, Dr. A. Pandikumar, for sharing such valuable insights with us today. It was really informative session, sir. Thank you, sir. Your session has been truly enlightening and has given us new perspectives on the topic photoelectrocatalytic water splitting, and especially about the green hydrogen transport vehicles. We are deeply thankful for the time and effort you have taken to be with us and enrich us with our enrich our faculty development program. And thank you, sir, for answering the queries with a clear explanation. Thank you so much, sir.
Thank you, madam. Thank you for the opportunity.
Thank you. And participants, you can fill the feedback link given in the chat box. And the next session will be happen sooner, so please wait. And around a few minutes, the next speaker will join. So participants, within 5 minutes, you can fill up the feedback link, and we'll proceed with the next session soon. Yes, it gives me immense pleasure to invite our distinguished resource person, Dr. S. Nenes Nirmala Jyoti, Assistant Professor of Physics, Loyola College, Chennai. She has completed his MPhil degree at Bharathasan University in the year of 2024. She has completed his PhD degree at the Madras University in the year of 2011. And she has 20 years of UG and PG teaching experience in Loyola College. And also, she has recorded research interest in nanomaterials for 20 years. She has published 24 articles in high-impact international journals with a good number of citations. And she also has presented numerous papers in international and national conferences. Currently, she has guided 4 PhD candidates and 3 were currently pursuing their research under her supervision. Her areas of specialization are bioactive functional materials, nanocomposites for drug delivery applications, terahertz crystals, and biological activities. Now, with great honor, I invite our respected speaker, Dr. N.S. Nirmala Jyoti, to take the session forward. Welcome you, ma'am.
Thank you, ma'am, for the nice words of introduction.
Thank you, ma'am.
I'm going to share my screen. Kindly check it and confirm, madam.
Okay, ma'am. Sure, ma'am. Yes, ma'am. It is visible, ma'am.
Yeah, yes, ma'am. Thank you so much, ma'am.
Thank you, ma'am. Thank you.
Good evening, everyone. It is my honor with the pleasure and privilege to convey my good wishes to the principal and other officials, the head of the Department of Science and Humanities, and special congratulations to the conveners, coordinators, and also the entire organizing team for planning this wonderful faculty development program on advancement and application of smart materials in environment and technologies, which is pioneering field in recent days. So now, more specific to the topic, smart material synthesis techniques, which is given to my presentation now. The plan of the talk includes what are smart biomaterials, historical progression, key characteristics, types and application, biofabrication innovations, classes of biomaterials, challenges, future directions, and summary. What are smart biomaterials? So these biomaterials are actually nanostructured materials which contribute to the fabrication of the diagnostic devices for various medical applications. Then these smart biomaterials, these are the emerging class of the materials that can respond to the external stimuli with the large discontinuous changes as shown in their properties. And they have been designed to act as an on and off switch. It could be act as the another alternative for the various mechanism, techniques, chromatography, immunoanalysis, drug delivery technologies, gene therapy, drug diagnostics, biosensors, and for artificial muscles. So these smart biomaterials are very significant in all biomedical field applications. Now coming to the historical evolution of the smart materials. Historically, these biomaterials will be on different types, and early biomaterials includes gold, iron, brass, glass, wood, and bone. The major properties of the biomaterials of the gold, they are malleable, inert metal, does not oxidize, and it will find a lot of application in dentistry. Then coming to the iron and brass, as we all know that they shows high strength and it could be used for rejoin the fractured femur. Then glass, which is a very common active biomaterial, and it is for the hard ceramic. It is used for the eye glasses. Then for wood, it is a natural composite and which is high strength to weight. It could be used for limb processes. And for bone, it could be the smart biomaterials can act as a natural composite due to their excessive biocompatibility. So as we have seen about their history, now we are moving on to the evolution of the smart biomaterials. As I said earlier, the smart biomaterials could be on 3 different generations as they are classified since 1950s, since 1980s, since 2000 onwards. And they aim to achieve the goal as a bioinertness, bioactivity, and they are used now recent days as regenerative functional tissue because of their high mechanical strength and biocompatibility. Now let me move on to the discussion about their 3 different types of the biomaterials which are classified under first generation, second generation, and third generation, so on. So the first generation biomaterials are usually, they are called as ad hoc implants. They are specified by physicians using very common and borrowed materials, and the requirements were used to find a suitable physical property and to match those of the various tissues with a minimal toxic response to the host So they are biologically inert or nearly inert materials which are used to reduce the corrosion and to minimize the immune response and also against the foreign response. So they are actually called as a bioinertness materials. Few examples includes gold fillings, wooden teeth, polymethyl methacrylate, dental processes, that is for artificial teeth, implants, steel, gold, ivory, and for bone plates, etc. So these are the first class of the first generation biomaterials. So as we move on to the second generation biomaterials, these shows a high bioactivity. So the first generation biomaterials are effective on the inertness. So now we are just moving on to the second level of bioactivity. So these biomaterials are actually engineered implants using common and borrowed materials with biopolymer composites, and they are developed through the collaborations of physicians along with the engineers. They show high bioactivity. So the second generation biomaterials are extensive characteristic features of the bioactivity. So a bioactive material is one that elicits a specific biological response as the interface of the material, which results in the formation of the bond between the tissue and the material. So few examples include heart valves and pacemakers. Now coming to the third generation biomaterials, and we are living in the era of third generation biomaterials. So this generation biomaterials introduces the idea of regenerative medicine and for the personalized medicine. So biomaterials, they are capable of stimulating one or more functions of the cells which are forming the basics of the tissue, muscle, or cartilage through proper signaling and to encourage the regeneration of these tissues. Few examples include cell matrices for three-dimensional growth and tissue reconstruction, which is the recent advancement in the medical field as a personalized medicine. So the third generation biomaterials are recently used in organ implants and also on different biomedical field applications. So the tissue engineering involves the use of the molecular and cell biology technology, combines the advantage of material science and processing to produce tissue regeneration in situations where the patient's cells cannot regenerate over the time. So we have studied about the history and evolution of the biomaterials. The third generation biomaterials are highly advantageous compared to the first and the second generation biomaterials. So this figure actually gives an idea about the biomaterials, how they are used in application as a joint replacements, hip replacement, heart valves, and also for the blood vessels, cochlear replacement, contact lenses, for dental implants, and also for the skin repair devices. Now coming to the classification of the biomaterials. So the synthetic biomaterials, they are classified into 4 different categories, namely metals, semiconductor materials, ceramics, and polymers. So the metals usually found as the application in orthopedic screws and dental implants. As we all know that for the semiconductor materials, they could be used for the implantable microelectrodes and also for the biosensors. Then the material with high thermal stability, they are ceramics. They could be used as for the dental implants and also for the bone replacements. Then coming to the polymers, they are very good in drug delivery devices, then skin, cartilage, ocular implants. So these are the major classes of the synthetic biomaterials which find the lot of applications. So how do the smart biomaterials respond towards the external stimuli? Usually these biomaterials shows effective property response on the external stimuli like physical stimuli, chemical stimuli, biological stimuli. And this material shows The improved finds a lot of application in tissue engineering, immunoengineering, and drug delivery applications. So this figure actually gives an idea about how do these smart materials, bioactive materials, are exposed towards the external stimuli, and they are effective with chromoactive, oxygen, water, ions separation, redox reactions, and for pH sensitive, then they shows high performance and reaction with glucose molecule, enzymatic reaction, ultrasound, then with high response or high sensitive towards magnetic field, electric field, temperature, and light sensitive materials. So all smart materials are effective on the external stimuli for physical stimuli, chemical stimuli, and biological stimuli. So now coming to the key characteristics of the smart biomaterials. This smart biomaterials possesses several properties which are very unique for their biomedical applications. So here I have included the few which are very basic and responsive. The key characteristics of the biomaterials, that is responsiveness, biocompatibility, biodegradability, and tunable properties. What is responsiveness of smart biomaterials? As we discussed earlier, they are responsive towards the specific stimuli, either physical stimuli, chemical stimuli, or biological stimuli, and they could interact with the biological systems in a controlled manner. So that is why they have preferred for the responsiveness activity, since they can easily adapt with the living tissues. Then biocompatibility. So these smart biomaterials should be biocompatible because they should not cause any harmful effect to the living tissues or cells. Then biodegradability. As we are aware of that, these materials should be able to degrade over the period of time with enzymatic or hydrolytic processes to avoid the accumulation in the body, that is to reduce harmfulness. Then tunable properties. So these biomaterials are preferred only because of their specific tunable properties like stiffness, porosity, and surface geometry with a specific chemistry which can be tuned for various applications. Now coming to the types of smart biomaterials, as we discussed earlier, this figure also shows their extensive response towards the physical stimuli, chemical stimuli, and biochemical stimuli. So within their environment, they have garnered a significant attention in the biomedical community, leads to the regenerative medicine, which is the patient-specific treatment. So coming to the biochemical stimuli, the smart biomaterials shows extensive response on the reaction towards glucose molecule, DNA, protein, and enzymatic reaction. And it also to be studied with respect to the physical stimuli changes on magnetic field, light, electric field, and temperature, along with the chemical stimuli responsive on gas, ion, and also towards the enzymatic reactions. Now, moving on to the types of the smart biomaterials. Again, we have just giving the importance towards their responsiveness on their stimuli responsive as physical stimuli and chemical stimuli, temperature sensitive, light sensitive, and magnetic field sensitiveness could be studied under the physical stimuli responsiveness of the smart biomaterials. Then they are pH sensitive towards the drug delivery application. Then enzymatic responsive, ion responsive could be studied under chemical stimuli responsiveness of smart biomaterials. Now we are moving on to the discussion on one by one. Let us begin with the physical stimuli responsive biomaterials. So how do the smart biomaterials respond on the temperature variation? Examples include thermoresponsive hydrogels, which either contract or swell in response to the changes in temperature. This can be used for the controlled drug release or in temperature variation could be used for the implants. So we can study about the drug loading efficiency, releasing efficiency, and also the encapsulation efficiency of the nanocarriers along with the drug molecules. Then about the light sensitive materials that respond to light exposure, they are often utilized for triggering the release of the drugs towards the activating the cellular processes. Then magnetic field sensitive, the biomaterial that can be guided or manipulated by magnetic field, they are useful for the targeted drug delivery in cancer therapy or in magnetic resonance imaging like MRI studies or in hyperthermia treatment, which is used in cancer patients. Now coming to the chemical stimuli responsive biomaterials. So these materials are sensitive towards pH, enzyme, and ion separation techniques. As the smart biomaterial that change their properties or functionality, which is based on the pH change, it is widely used in the targeted drug delivery to the targeted tumor sites cure and also for the treatment purpose, and they could be called as a pH sensitive biomaterials. Then enzyme responsive, this material that degrade or they can release drugs in response to the specific enzymatic reaction on targeted drug delivery in specific tissues repairing or to modify the conditions of the damaged tissues. Then ion responsive materials, these biomaterials that can change their properties, which is based on the biochemical reaction, which is accompanied with the ion concentration, potentially useful for the targeted drug delivery or in ion sensitive sensors. So now we are moving on to the specific class of these smart biomaterials, which are called as a green biomaterials. So the green biomaterial, they have emerged as a revolutionary solution in the sustainable and eco-friendly alternative to the traditional materials. Why these green biomaterials are preferred for research and for other advancements? These recent advancements in the field have led to the various biomaterials which are considered as a renewable sources such as plants, algae, and agriculture waste. These materials reduce dependence on fossil fuels and minimize the environmental impact by being biodegradable and non-toxic. Innovations in biopolymer engineering, nanotechnology, and biofabrication techniques enhance the properties of green biomaterials, making them suitable for various biomedical applications. From packaging and textiles to biomedical devices and construction materials, green biomaterials, they have led to the big way for a more sustainable and circular economy. This slide shows the few examples for the green biomaterials, which are considered for their effectiveness in antimicrobial property, like natural antimicrobial agents, biopolymers with antimicrobial properties. So in the first figure, it is given with honey comb, then with the pomegranate seeds, plants, then with wheat or rice husk, which are known for their excessive antimicrobial property. So they are considered as a green biomaterial, which are very good smart biomaterials. Then coming with the biopolymers, there are some materials with the shells like they are with the chitin and chitosan. They are considered as a common source of the biopolymers like say the crab, snail, and their shells could be used for their effectiveness on antimicrobial property. What are the potential applications of the smart biomaterials? As we discussed earlier, they are used effective in drug delivery vehicles, tissue engineering, biosensors, and medical devices. Drug delivery system. Drugs, they are played a pivotal role in alleviating illness and its well-being of the human and extending both for human and animal lifespan. Drug delivery system, It describes a technology that carries drug over the nanomaterials as a drug carrier. It could be on the effective treatment throughout the body. What are the drug delivery devices? The drug delivery devices are specialized equipment designed to circulate the therapeutic substance to patients in a precise and controlled manner. It can take various forms, including drug-loaded nanoparticles, liposomes, missiles, implantable devices, and transdermal patches. Tissue engineering, where the smart biomaterial plays a vital role. It is the use of combination of cells, tissues, and the material methods suitable with biochemical and physiochemical factors to improve or replace the biological functions of the tissues. The term has also been applied to efforts in order to perform the efficient biochemical functions using cells within artificially or an effective systems for artificial pancreas or to the bioartificial liver production. Tissue engineering covers a broad range of application where the term has been used to represent application that to repair or to replace a structural tissues like bone, cartilage, blood vessels, bladder, using the smart biomaterials due to their key characteristics as a biocompatibility and effective responsiveness. Why do the smart materials are preferred for the medical diagnostic devices? The simplest and one is the biosensor. There are different types of the biosensor. And the man which is shown in the picture, his name is Leland Clark, who invented the biosensor in the year 1954. And the term biosensor is device as a sensor incorporating the biological element, which is to be active on the enzymes, antibodies, receptor proteins, nucleic acids, cells and tissues as a recognition element, and it is coupled to the transducer. It can detect or records and transmits the information regarding the physical change or process, and it determines the presence and concentration of the specific analyte in the test solution. And the biosensor, the first biosensor where the oxygen electrode that could be used for the blood oxygen level testing device by Leland C. Clark, and which is made the major contribution to avoid surgery, and it is a very safer mode, and it is more successful for millions around the world. There are different types of biosensors are available even as a diagnostic as well as for the therapeutic devices. Properties of the biomaterials: adequate mechanical strength, high corrosion resistance and biocompatibility, high wear resistance, low friction, mechanical compatibility, and so on. So coming to the surface properties of the biomaterials, these surfaces can be comprised of different geometry, chemistries with atomic, supramolecular, and macromolecular geometry. The surfaces may be structurally or compositionally inhomogeneous with their phase-separated domains or micro-contact printed lanes, which are more specific for application. The surfaces may be inhomogeneous with the depth into the specimen, or it could be overlaid with a thin film. So the surfaces can be either highly crystalline or disorderous. So depending on the particular application, we can just study about their surface property, which is more specific for their requirement. Now coming to the mechanical properties of the biomaterials, it shows elastic modulus, hardness, fracture toughness, fracture strength, and improvement. So coming to the elastic modulus, the smart biomaterial measures stiffness, that is the ratio of stress to strain, and to match with the natural tissue to avoid the implant failure. So this biomaterial shows extensive elastic modulus, so which is very important for the movement. Tested via nano indentation and laser ultrasonics to study about the elastic modulus of the material. Then coming to the hardness studies, it shows the resistance to wear and deformation, crucial for aberration resistance in implants, then micro and nano indentation methods used. Then coming to the fracture toughness studies, it prevents crack propagation, vital for clinical reliability, enhanced with additives like zirconia. Then it shows high fracture strength, maximum strength. Then it is very useful for the brittle materials to avoid the flaw control, and it influenced by the porosity and flaw size. Then improvements could be done on the ceramic materials for crystallization and reinforcements in order to achieve the strong, biocompatible, durable biomaterial for various surgical applications. Now let us moving on to the thermal property of biomaterials. The thermal properties of the biomaterials can have the significant effect on the performance of the material with regard to the implantation and interfacing with biological tissues. So the thermal property of the material, they are essential to evaluate the thermal behavior of the solid, which consists of heat capacity, thermal expansion, thermal conductivity, thermal stability, specific heat, melting point, and thermal shock resistance. So the thermal property refers to the response of the material to the application of heat as a solid that absorbs energy in the form of heat, and its temperature rises within an increase in the specific dimensions, which could be used for implantation and interfacing with the biological tissues with biocompatibility. Now coming to the optical properties of the biomaterials. The optical properties of the biomaterial determine how do these biomaterials interact with the light, which is very important in biomedical applications, and how these materials absorbs the light, and the light could be transmitted through the material, could be used for wound healing, like chronic wound healing as it is shown in the figure in the LED matrix, and it is used with the reflector, then thermal diffuser, biosensor, then optical diffuser. So this smart material could be used as a patches, and they could be used to heal the chronic wounds due to their extensive properties on absorbability, color, luminosity, photosensitivity, reflectivity, refractive index, scattering, transmitters, and electromagnetic radiations response makes these biomaterials are effective for the patches to heal these chronic wounds. Electrical properties of the biomaterials. So the biomaterials can permit or resist the flow of electricity by employing the electric property of the material. Biomaterials with electrical properties such as conductive, piezoelectric, or dielectric, they are utilized in tissue regeneration, energy storage, and biosensing for healing, energy capture, and signal direction. They show their high response on resistivity, conductivity, dielectric strength, thermoelectricity, and temperature coefficient of resistance. These properties make this biomaterial as effective on electric property. Then moving on to the magnetic property of the biomaterials. Magnetism also has a strong role to play in their bio applications. Magnetic properties change dramatically with respect to the particle size beyond a critical limit or critical size, which can make them to work on the single domain and subdomain regions. So below the critical size, it shows with the super paramagnetic properties. This makes the smart biomaterials could be extensively for the magnetic bio separation, MRI contrast agents, and for other bio applications like bioseparation. The super paramagnetic materials are considered to be superior to the ferro and ferrimagnetic particle due to their absence of remnants in the magnetic field. Since a magnetic material exhibits the magnetic properties extensively only in the presence of magnetic field in bioseparation, they could be removed from suspension by applying the magnetic field. So after separation, it is easy to redisperse them in the homogeneous mixture in the absence of magnetic field, which is important in the hyperthermia treatment as for the cancer patients. So now we are moving on to the special case of the biomaterials as the metallic biomaterials and magnetic biomaterials. So the metallic biomaterial, they are most dominant group of the materials. They are highly used for implantation of the tissues or for organs. They are engineered systems developed to provide the internal support to the biological tissues. They are used largely in joint replacements like artificial joints and for bone plates and screws, then for the dental implants for artificial teeth, then stents and orthoperiodic fixation. So the metallic biomaterial shows high strength. That's why they are preferred on various applications. In addition, they are also used in cardiovascular devices like artificial heart valves and other major components of the heart assistant devices like vascular stents, neurovascular devices, and that has been gained for various attention to the physician. The good electrical conductivity of metal favors their use in the neuromuscular stream, and they are most common used example in cardiac pacemakers. Metallic biomaterials may be employed not just as a replacement for a failed heart tissue, but they are also used in the reconstruction of the soft tissue such as blood vessels. So this figure actually shows how do this metallic biomaterials could act as orthoperiodic implants, and before and after surgery, how do they have been just acting for their biocompatibility and for their effective responsiveness towards the organ acceptance, then for dental implants, for artificial teeth, then for cardiovascular devices as stents, then cardiovascular devices as a pacemaker causing, then external fixation systems. So the metallic smart materials are preferred on this vital application by physicians. Then moving on to the next important class of the smart biomaterials, they are the magnetic biomaterials. So the magnetic biomaterials, they are materials that possess magnetic properties, and they are extensively designed to interact very safely and effectively with all biological systems, with the cell, tissue, and so on. So they are often composed of the magnetic nanoparticles such as magnetite or magnemite. Sometimes they are embedded in biopolymers or hydrogels. These magnetic biomaterials are actually super paramagnetic because they carry the magnetism only in the presence of the magnetic field, and they don't have the capacity to retain it. So these magnetic biomaterials are very safer and secured for their usage in human body. So this magnetic biomaterials can respond to the external magnetic field, which is very useful for targeted drug delivery, MRI imaging, cancer therapy, that is hyperthermia treatment, and for tissue engineering. So far we have studied about the metallic biomaterials and magnetic biomaterials with their property and application. So now coming to the key characteristics of the magnetic biomaterials: magnetic responsiveness, super paramagnetism, biocompatibility, and their functional effectiveness, nanoscale size, thermal conversion, colloidal stability, then their structure as a scaffold or composites. So these materials react to external magnetic field, and they do not carry the residual magnetism, which is very ideal for biomedical use, very safe and non-toxic in biological environment, that is highly biocompatible, then functional alternative with the nanoscale size enhances circulation, uptake of the molecules and bioavailability, thermal conversion. They can generate heat for cancer hyperthermia, and which is very important to cure the or to remove the damaged cells. Then for the colloidal stability, they can remain well dispersed in fluids, then structure as a scaffold in composites. So this figure shows some of the major advantages of the magnetic biomaterial. They are used in tissue engineering, biosensors, medical diagnostics, as a magnetic resonance imaging, contrast agents, then targeted drug delivery as a nano carriers for drug and to calculate their releasing and loading efficiency. So now let me move on to the major aspect of this smart materials as a biofabrication techniques of this smart biomaterials. What is biofabrication? So the biofabrication is an emerging technology which encompasses the diverse range of the physical, chemical, biological, and engineering methodologies to assemble biologically sub-derived components, leading to the development of models, devices, systems, and products with broad applications. As do we integrate the smart materials into the biofabrication process, let us make it possibility to enhance their functionality and enable them to be utilized in various fields as a tissue engineering and regenerative medicine, exclusively for the personalized medicine, drug screening, and pharmaceutical development, so biosensors and bioanalysis, synthetic biology, and biocatalysis. One of the primary objectives of the biofabrication is a precise spatial control and high resolution generation of three-dimensional structures composed of living cells that either are with the biopolymers or biomaterials. The introduction of smart biomaterials with the stimuli responsive or autonomous response has significantly influenced their field of biofabrication. The three major potential transformative applications of the smart biomaterials in biofabrication techniques are classified into 4D bioprinting with the smart biomaterials, chaotic printing with the smart biomaterials, smart biomaterial films. So now let me move on to this one by one. 3D print, smart biomaterials. As you are aware of the fact, 3D bioprinting technology. So the bioprinting is defined as a printing of structures, the biostructures consisting of living cells, biomaterials, and active biomolecules, as shown in the figure, as solution for organ shortage, and it is a very significant potential for drug delivery and cancer studies. What is the bioprinting technology? Bioprinting of the tissues is constructed using bioink. What is a bioink? These bioinks are very crucial for bioprinting, and they are typically composed of the biomaterial cells and growth factors, natural and synthetic polymers, as well as peptides. They are commonly used as a bioinks, but the choice of the bioink depends on the specific application and the desired property of the printed structure. So the bioink refers to the cell-laden fluid material. They might include biomaterial, cells, growth factors, microcarriers, etc. Usually hydrogel is preferred as an attractive material for bioprinting. This slide shows the types of the bioprinting: inkjet bioprinting, micro extrusion bioprinting, laser assisted bioprinting. So now let me see this one by one. What is inkjet bioprinting? Here the bioink is jetted onto a substrate using the thermal, electrostatic, or piezoelectric forces. So here it is given in the figure, thermal and piezoelectric. You could see that in the figure as a heater, vapor bubble, piezoelectric activator. It is used with the advantage of high speed, relatively low cost, compatible with the living materials. Few disadvantages include with the limited resolution, but it is potential for cell damage due to the heat or pressure. The second technology is a micro extrusion bioprinter, mnemonic, piston, screw. It is associated with the wall. These are the three major components. So here the mechanism follows with the bioink, which is pushed through a nozzle, either by gravity or a piston or a screw mechanism. And it is suitable for a wide range of bioinks, including those with a higher viscosity. Few disadvantage is it is a very slow process than inkjet it could also be having the disadvantages of lower resolution. And the recent advancement included with the laser-assisted bioprinting. So it shows a high resolution because a laser beam, highly monochromatic, is focused on the bioink film used to create a bubble that propels a droplet onto the substrate as shown in the figure. You could see all the three figures where the laser-assisted bioprinting shows high resolution and it is precise control over droplet placement, but it has an disadvantage of the more expensive and complex than other methods. So this slide also shows the different mechanism under the extrusion-based bioprinting, inject-based bioprinting, laser-assisted bioprinting, where in the first part, the cells could be associated with the polymers to create the cross-linker molecule, which can act as a bioink, and it is injected into the tube, and it is to be done through activator with either gravity, piston or a screw mechanism as a piezoelectric activator or heater. Then it is just associated with the energy absorbed layer through the laser pulse, and from the donor slide, the droplet molecules could be just assembled as a scaffold, which could be used for in vitro disease model, or it is used for the various tissue engineering applications as the regenerative medicine. Then for the polymer-based bioink could also be preferred, and the choice of the bioink and the cross-linker molecule, it is purely based on the application. So this figure actually gives an idea about the various stages of the bioprinting process. So under continuous process of the bioprinting, there are different stages A, B, C, D, and E. It is given. So in the first figure, it is rectangular shaped bioprinting has been done. Then the second figure, zigzag patterned. Then third figure, circular shape. Then the fourth figure, D, that is random shaped bioprinting is taking place. And E, last figure, it is a ring-shaped printed structures with the 2 layers of multicellular aggregates could be visibly shown in the figure. So bioprinting is very important technique on the skin replacement or for organ implants. Now 4D bioprinting with the smart biomaterials. The 4D bioprinting extends 3D bioprinting by incorporating time-dependent shape transformation into the printed constructs. This fourth dimension, time, is activated through the environmental stimuli like pH, temperature, moisture, magnetic field, or light. So it is based on the various design principle to enrich the smart biomaterials for shape memory polymers, hydrogels, using the design principle on programming the smart material to be sensitive on the printing, then combining multiple materials on different stages to involve the effectiveness on various regions. Then about the stimuli are either internal or external. If it is an internal, then it is enzyme secretion or within the presence of ionic environment. If it is an external stimuli, then one such example is an infrared light. So this figure actually shows the effectiveness from 3D bioprinting to 4D bioprinting. So the first figure is the earlier one, what we have discussed through the inject bioprinting. Then 3D bioprinting, it has been just incorporated with the cell encapsulated scaffold used to achieve the particular model, and it is activated on the various stimuli like physical stimuli, chemical stimuli, and biological stimuli with the temperature, magnetic field, electric field, and light. Coming to the chemical stimuli, these scaffolds are responsive on pH. Then they might have been studied for the enzymatic reaction. And finally, we can achieve the 4D bioprinting for the required scaffold. Applications of 3D, 4D bioprinting methods. Tissue engineering, dynamic scaffolds as shown in the figure. They can evolve like real tissue, drug delivery, the time-controlled release in specific locations for chronic treatment, implants like self-unfolding stents or catheters that adjust after insertion, and finally they could be used for soft probactors like bioactivated movement in response to the environmental changes, which is a recent advantage of this smart biomaterials by 4D printing technology. Chaotic printing with smart biomaterials. Chaotic printing introduces the complex nonlinear mixing patterns during extrusion. It exploits chaotic flow dynamics to achieve a high-resolution spatial distribution of multiple components, example, cells, polymers, and biomolecules. The materials and tools to be used: shear thinning bioinks, multi-material cartridges, computational modeling. Then key advantages of this method: controlled hydrogenicity, increased functional gradient, nozzle engineering for effective scaffolds. Coming to the application of this chaotic bioprinting, vascular tissue printing as shown in the figure, like 3D printed living lung tissue, mimics natural alignment of endothelial and smooth muscle cells. Neural tissue scaffolds achieves patterning of neural versus glial cells. Bone cartilage interfaces that can generate greater zones of hardness with elasticity. Now, the recent advantage of this type of biomaterial techniques include smart biomaterial films. They are nothing but thin flexible films composed of smart biomaterials that can sense, respond, or adapt to their environment. These films are typically used as coatings, barriers, or functional surfaces. So the fabrication techniques includes spin coating, layer by layer assembly, solvent casting, electrospraying, or inkjet printing. In order to be effective with the functional components, antimicrobial peptides are nanocarriers to prevent infection, extracellular matrix for biomimic photosensitive groups in order to allow these smart material for controlled responsive and a specific wavelength. The major application of this smart biomaterial films includes wound healing dressings, because they release antimicrobials or drugs on contact with the external wound exudate. Flexible biosensors, they can detect biomarkers or physiological changes. Implant coatings reduce immune rejection and enhance biocompatibility. Then drug-eluting films for controlled dosage and timing. So in the figure, it is given with the traditional wound dressings along with the comparison towards the smart biomaterial films. They could act as the traditional gases that are replaced with the impregnated gases, bilayer or multi-layer films, foams, hydrogels with hydrocolloids, and multi-layer structures. So this figure explains how this biomaterial can react with the cells to produce a cell containing biomaterial that can be injected to the organ in order to be functional regenerative for personalized medicine. What are the challenges on the smart biomaterials? Ensuring that biomaterials are well tolerated by the body and don't trigger adverse immune response is very crucial. Many biomaterials degrade over time, which can affect their performance and lead to complications. Developing materials with predictable and controlled degradation rate is a key challenge on this advanced technique. Replicating the intricate structure and function of natural tissues in vitro remains the significant hurdle. Producing biomaterials on a large scale and at a reasonable cost is essential for widespread clinical use, which is a highly challenging one. Future direction. To develop patient-specific biomaterials for targeted therapy, apply 3D bioprinting to create complex, customized scaffold for regenerative medicine and for drug delivery, using bio-based, biodegradable material to promote sustainability in healthcare sector, design multifunctional materials for drug delivery, imaging and therapy, to create hybrid biomaterial with integrated electronics for advanced biosensing and for treatment, then for diagnostic devices. Now coming to the summary of the smart biomaterials. Definition: advanced biomaterial that respond dynamically to internal or external stimuli like physical stimuli, chemical stimuli, and biological stimuli. On view example includes their sensitiveness on temperature, light, magnetic field, enzymes, historical progression, progressed from bio-inert as the first generation to bioactive materials, second generation, then to the third generation as for the regenerative medicine for the biomaterial progression. Key properties of the biomaterials includes responsiveness, biocompatibility, biodegradability with tunable mechanical properties. Types of the biomaterials shows effective stimuli responsive on physical stimuli, chemical stimuli, and biological stimuli with the specific application to the introduction about the green biomaterials which are renewable, biodegradable, and it is achieved from eco-friendly sources. Coming to the applications of smart biomaterials includes drug delivery, tissue engineering, biosensors, implant coatings, wound healing, dressings, flexible biomedical films. Biofabrication innovations include 3D printing, 4D printing, time-dependent shape changes, chaotic printing with biomaterial films. Special classes includes metallic biomaterials and magnetic biomaterials. They could be used on various applications as orthopedic, dental, cardiovascular implants, MRI contrast agents, hyperthermia treatment, targeted drug delivery. Then coming to the challenges, ensuring biocompatibility, controlled degradation, cost effective with large scale production, and replicating complex tissue structures for scaffolds. Future direction, patient-specific customization, multifunctional integration, advanced bioprinting, and sustainable material development. As we move on to the acknowledgement part, grateful to the organizers of the team on advancement and application of smart materials in environment and technologies program, which is conducted by the Macetatalfdp College of Engineering and Technology for this great invitation as to be the part of this program. My sincere appreciation to the organizing team of the Department of Science and Humanities for their warm welcome and with the introduction with the support. Gratitude to all my colleagues from the Department of Physics, Loyola College, Chennai for their encouragement and research support. Special mention to the research scholars, Trisma Yunus and Francis Disha for their valuable ideas and suggestions for their hard work. Thanks to the faculty members, participants, research scholars, and students. Heartfelt thanks to my co-presenters for their insights throughout the session. A heartfelt thanks to the great opportunity to share my knowledge, and also you are most welcome for the future collaboration in biomaterials and sustainable technologies. Thank you one and all.
So participants can ask your questions now if you have any doubts and queries.
Yes, you can also in the chat box. I am happy to share.
Participants can ask your queries now. Please unmute your audio and you can ask now. So if there is any no queries, means we can wind up the session.
Thank you, participants.
So on behalf of our institution, Macetatalfdp College of Engineering and Technology, I extend heartfelt thanks to our dynamic resource person for the inspiring and informative session. Your words have enlightened with the knowledge of smart materials from their history, classification, types, applications, and properties to their synthesis and challenges also. It was really an informative session that gives a clear picture of smart materials. We are deeply thankful for your presence and contribution for this faculty development program. And thank you so much, ma'am, for your contribution. Thank you, ma'am. So we have come to the end of the session. Thank you, participants, for your active participation throughout the both sessions. So tomorrow, the first session will start sharply at 6 p.m. and the second session will be at 7:30 p.m. All the participants are asked kindly to join the program as given. The time is given in the schedule. Thank you all. The feedback link will be given in the chat box. Please fill your feedback. So is there any participants still with not completing the feedback link?